Welcome to our presentation on factor analysis in EViews. Our goal is to guide you from the underlying theory to practical application using the Holzinger-Swineford data. Exploratory factor analysis is a statistical method used to uncover the underlying structure of a relatively large set of variables by explaining covariance relationships amongst observed variables in terms of a smaller number of unobserved variables. We will cover the entire workflow, including object creation, factor rotation, and the generation of factor scores. For instance, if you have 20 survey questions about customer satisfaction, factor analysis can help you discover if these questions actually measure a smaller number of underlying concepts, like service quality, price perception, and product usability. So, why do we need a technique like this in the first place? The answer lies in a common problem in data analysis, the curse of dimensionality. The core problem we face is complexity. When we have many variables, the web of correlations between them can be overwhelming and noisy, making it difficult to see the underlying patterns. Factor analysis provides a solution by simplifying the structure. It groups correlated variables together, representing them with a smaller number of latent factors. The main goal is parsimony. We want to reduce the number of variables while retaining the maximum amount of significant information. It's about finding a cleaner, more interpretable structure in the data. Imagine trying to understand a student's academic ability by looking at their scores in 30 different subjects. It's complicated. Factor analysis could simplify this by showing that these 30 scores can be largely explained by just 3 underlying factors: quantitative ability, linguistic skill, and creative talent. To achieve this parsimonious solution, we follow a structured process. Let's look at the roadmap for conducting a factor analysis. The process begins with our input data, which can be a group of series or a pre-computed covariance matrix. We then check a key assumption by examining the correlation matrix to ensure the variables are sufficiently correlated for analysis. A crucial choice is the extraction method. We'll discuss the difference between principal factors and maximum likelihood, or ML. Next, we must decide how many factors to retain. Common methods include the eigenvalue greater than 1 rule, the scree plot, and the map test. After extraction, we perform rotation to make the factors more interpretable. We can choose between orthogonal methods like Varimax or oblique methods like Promax. The final output gives us factor loadings, which show the relationship between variables and factors, and factor scores for each observation. Think of this roadmap like a recipe. Each step is a decision. Choosing maximum likelihood extraction and Varimax rotation is like choosing to bake a cake instead of grilling a steak. Both use the same ingredients, data, but the choices lead to different specific outcomes. Before we dive into these steps, let's formalize the underlying statistical model that makes this all possible. The common factor model is expressed mathematically as x equals mu plus lambda f plus e. Here, x represents the vector of our observed variables. The term lambda f represents the common variance. Lambda is the matrix of factor loadings, which are like regression coefficients, and f is the vector of unobserved common factors. The term e represents the unique factors, or error. Unlike PCA, principal component analysis, factor analysis explicitly models this measurement error. This means that total variance of each variable is decomposed into 2 parts: common variance, called communality, which is shared with other variables, and unique variance, which is specific to that variable plus random error. First, our variables must be metric, meaning they should be on an interval or ratio scale. Normality is a requirement for certain estimation methods, specifically ML, or maximum likelihood. If your data is not normally distributed, the principal factors method is a more robust alternative. You need a sufficient sample size. While there are various rules of thumb, having more observations than variables is critical. In our case study, we have an N of 145. The relationships between the observed variables are assumed to be linear. Most importantly, the data must be factorable. This means the variables must be correlated with each other. If there are no correlations, there are no common factors to find. We can formally check this using Bartlett's test of sphericity. Factor analysis requires correlated data. If variables are independent, there are no common factors to find. As a rule of thumb, check the correlation matrix first. If correlations are low, less than 0.3, factor analysis may not be appropriate. The factor loading indicates the correlation between an observed variable and a latent factor. You can think of it as a regression coefficient. A high loading means the variable is strongly representative of that factor. As a rule of thumb, loadings greater than 0.4 are considered significant. In the table, test score A has a high loading of 0.85 on factor 1, but a low loading of 0.12 on factor 2. Communality represents the proportion of a variable's variance that is explained by the extracted factors. It's the sum of the squared loadings for that variable. For test score A, the communality is 0.76, which means 76% of its variance is captured by our two-factor model. A high communality indicates that the variable fits the model well. Looking at the table, test scores A, B, and C load highly on factor 1, while D and E load highly on factor 2. This suggests factor 1 might represent one skill, for example, verbal, and factor 2 another, for example, spatial. The initial output isn't always this clear, however. Often, the initial unrotated solution is difficult to interpret because variables load moderately on multiple factors. This is where rotation becomes an essential tool for clarification. Rotation is a crucial step that simplifies the factor structure, making it easier to interpret. Importantly, rotation does not change the overall fit of the model. It only changes our perspective on the factors. The goal is to achieve a simple structure, where each variable loads highly on only one factor and has near zero loadings on the others. This helps us name the factors meaningfully. There are two main types of rotation. Orthogonal rotation, like Varimax, keeps the factors uncorrelated by maintaining a 90-degree angle between the axes. Oblique rotation, like Promax, allows the factors to be correlated by letting the axes tilt. This is often more realistic, as underlying psychological or economic constructs are rarely completely independent. Getting started in EViews is straightforward. First, select all the variables you want to include in the analysis from the work file window. The easiest way to start is to highlight your variables, open them as a group, and then create the factor object directly from the group menu by navigating to Proc and selecting Make Factor. EViews auto-populates the variable list this way, which is very convenient. In the Estimation tab, EViews defaults to maximum likelihood as the estimation method. If your data violates normality assumptions, consider using principal factors instead. For determining the number of factors, Valisser's MAP criterion is generally preferred for automatic selection, as it's often more robust than the simple eigenvalue greater than 1 rule. Finally, the prior communalities section defaults to squared multiple correlations, or SMC, which is a standard and effective choice. For our case study, we're using the Holzinger-Swineford data, specifically the Holzinger24.wf1 dataset, which includes test scores from 145 students. The main purpose of this case study is to analyze these test scores and identify if intelligence is a single, undifferentiated ability or if it comprises distinct skills. As shown in the table, we have categorized the variables into those we believe measure spatial abilities, verbal abilities, and a mixed category. Our core hypothesis is that we will find evidence of two distinct latent intelligences, spatial and verbal. We expect the variables to cluster into two distinct groups corresponding to these hypothesized abilities. For example, tests like visual, cubes, and flags 1 are expected to group together as spatial, while paragraph, sentence, and word mem are expected to form a verbal cluster. The paper 1 test, being mixed, might show loadings on both or be less clearly aligned.
This study is a classic example of using factor analysis to uncover the underlying structure of cognitive abilities.
After running the analysis with automatic selection, we get a scree plot, which graphs the eigenvalues against the number of factors. The elbow method is a popular heuristic. We look for the point on the plot where the curve flattens out. Here, the slope changes dramatically after the second factor, suggesting we should retain two factors. Velleser's map criterion provides a more formal test. In this case, the output explicitly states that the map criterion is minimized at two factors. Since both the visual evidence from the scree plot and the formal map test agree, we can be confident in our decision to proceed with a two-factor solution. On the left, we see the unrotated loadings. Notice that most variables have moderate loadings on both factor 1 and factor 2. For example, paragraph loads 0.45 on factor 1 and 0.38 on factor 2. This makes interpretation ambiguous. On the right, we see the results after an oblique rotation. The structure is now much clearer. Variables like paragraph, sentence, and word mem load very highly on factor 1 and near 0 on factor 2. Conversely, variables like visual, cubes, and flags 1 now load very highly on factor 2 and have near 0 loadings on factor 1. This clear separation allows us to confidently name the factors. Factor 1 is clearly defined by the verbal tests, so we can name it verbal ability. Factor 2 is defined by the spatial tests, so we can name it spatial ability. Before rotation, it's like looking at a blurry photo. After rotation, the image is sharp. For instance, the variable sentence goes from loadings of 0.48, 0.41 to a much clearer 0.81, -0.05. This confirms our initial hypothesis about the data's underlying structure. We can see this clarified structure even more starkly by visualizing the loadings on a graph. The loadings graph provides visual evidence of the clustering. Cluster check. Variables that measure the same trait will point in the same direction. Factor scores are numerical values that estimate each subject's standing on the latent factors we've identified. In our case, every one of the 145 students will receive a score for verbal ability and a score for spatial ability. The graph plots each student as a point in the factor space. For example, student A has a high score on the spatial factor, but an average score on the verbal factor. Student B is the opposite, with very high verbal ability. A key use of these scores is dimensionality reduction. We can now replace the original 7 test score variables with just these 2 factor scores in subsequent analyses, like a regression model. This is extremely useful for solving problems like multicollinearity, where the original variables were too highly correlated to be used together as independent variables. Suppose we wanted to predict students' future GPA. Instead of using all 7 potentially collinear test scores as predictors, we could use just the 2 uncorrelated factor scores, score 1 verbal and score 2 spatial. This creates a more parsimonious and stable regression model. In EViews, this is done via Proc, make scores, saves score 1 and score 2 to work file. Before we conclude our analysis, it's good practice to perform one final check to validate the quality of our model. A good factor model should explain the correlations observed in the data. The residual covariance matrix shows the correlations that are left over after accounting for the factors. In a well-fitting model, the off-diagonal values in this matrix should be very small, close to 0. This indicates that our factors have successfully captured the shared variance among the variables. The diagonal values represent the unique variance of each variable, the part not explained by the common factors. These are expected to be positive. This serves as a quality control check. If you find large off-diagonal residuals, it's a sign that the model is not a good fit for the data, and you may need to consider extracting more factors. Every action performed through the EViews graphical user interface, or GUI, generates an underlying text command. You can see these commands in the capture window. Using syntax instead of point and click is crucial for reproducibility. A script file ensures that you or anyone else can replicate your exact analysis perfectly, from object creation to rotation and scoring. The factor command creates the factor object. Here, f1.mln equals 2 creates a factor object named f1 using the ml method with 2 factors. You then use object-specific commands like f1.rotate to perform rotation, specifying parameters like t equals quartimax and oblique. f1.loadings displays the results of the factor loadings, and f1.makescores n2 score 1 score 2 generates factor scores for each observation, saving them as score 1 and score 2. Finally, you can access the results programmatically. For example, matrix loadings equals f1.loadings saves the loading matrix into a new EViews matrix object for further manipulation. Instead of clicking through all the dialogues again, you could simply save these lines of code in a program file. Running this file would instantly reproduce the entire analysis, which is incredibly efficient and reliable for complex projects. Thank you for joining our presentation on factor analysis in EViews. We have provided a list of references that were instrumental in this work, including foundational texts by Gorsuch, Harman, and Holzinger and Swineford. For more resources and to connect with us,